We're going to be looking at some applications of the impulse change of momentum relationship. Now, according to that relationship, the impulse is equal to the change of momentum. As an example, suppose that I drop this brick to the table. Now, in the collision, the brick underwent a change of momentum. That's its final momentum minus its initial. The final momentum is what it has now when it has come to a stop, so that's 0. The initial momentum is what it had at the instant that it hit the table, and that depends upon how far I dropped it from. Now, if I were to drop the brick on this cushion, its change of momentum would be the same as it were for the table, because the brick comes to a stop. That's its final momentum, which is 0. And its initial momentum is what it had at the instant it hit. And if I drop from the same height, that's the same as it was for directly on the table. What is different in these two cases is the amount of time that the collision lasts. In the case of the cushion, you can see that the cushion depresses. You can see the cushion compress, and that takes more time than if I drop it directly on the table. So you can see what the purpose of a cushion is. That's the cushioning effect that you get, is basically it's increasing the time that the collision lasts. When you walk across a carpeted floor, you have the same sort of a situation. For each step on the floor, you feel less force than if you were to walk across a concrete floor, for example, because the duration of each collision is less. Another example of that is when you jump from a height. When you hit the ground, as you hit the ground, you always bend your knees. That's essential if you want to protect your bones. Because by bending your knees, it makes that collision last a lot longer, and as a result of that, the force of the impact is less. If you didn't bend your knees, you'd do serious damage to your bones and to your joints. Now, we can apply the impulse-momentum relationship to another situation where, in fact, we want to make the force as large as possible. When you pound a nail, you want greater force, not less force. When I drop the hammer on the head of the nail, the hammer undergoes a certain change of momentum while it's colliding, from whatever it had at the instant it hit to 0 when it comes to a stop. So again, that side of the equation is fixed. So if I pound with the piece of wood on the table, my collision is going to last a lot shorter time than if I pound with my block of wood on the cushion. Obviously, you'd never try doing something like that. That makes the collision last too long, and so the force is going to be correspondingly small. You always have a hard surface underneath it. That makes the collision last for a shorter period of time.